Up to this point, we've focused on kinematics, which is how things move. What we're going to do now is transition to talking about dynamics, which is why things move. Talking about why an object moves means talking about forces and how they act on the object. Let's start by defining what a force is. Fundamentally, a force is an interaction between two objects. In simplest terms, a force is how one object pushes or pulls on another. Whenever we're talking about a force, there have to be two objects involved, one object that causes the force and the other object that feels the force. Because forces tell us how objects push and pull on each other, we care about not just the magnitude of the force, how hard an object pushes or pulls, but also its direction. Therefore, forces are vectors, and we will need to treat them as vectors when we work with them. Historically, the rules governing how forces act on an object to change its motion were initially formulated by Isaac Newton. We refer to them as Newton's laws of motion, and much of our focus over the next few weeks of the course will be on understanding and using Newton's laws. As a tribute to Newton, the SI unit for force is the Newton, which in base units is a kilogram meter per second squared. As an example, let's think about a simple scenario with a box sitting on a horizontal table. One way to categorize the forces we will deal with in this course is to describe them as either contact forces or non-contact forces. With contact forces, one object pushes or pulls on another through a contact interaction. So the first contact force we will talk about is the contact between surfaces, in this case the contact between the box and the table. You'll notice that there are two forces we could talk about from this interaction, how the box pushes down on the table and how the table pushes up on the box. Newton's third law will help us understand how these two forces relate to each other, but for the moment we will only be interested in the forces felt by the box. All the forces that we're going to draw in our diagram will be forces that act on the box. So in this case, we will only keep the force exerted on the box by the table in our diagram. When we talk about the force due to the contact between surfaces, there are two components of a contact force that we will keep track of: a normal force that is perpendicular to the surface and a friction force that points along the surface. In this case, with the box simply sitting on the surface, the force exerted on the box by the table is entirely perpendicular to the table, and we only have a normal force. Because the table is horizontal and the table sits below the box, that normal force points up. Let me make a brief point on notation here. For most forces, we will use a capital F to denote a force and a subscript to tell us what type of force it is. We will label the normal force in a vector diagram with a capital F and an N subscript. Friction is a little bit different in that we will use a lowercase f to label a friction force. There also happen to be two types of friction forces, static friction and kinetic friction. We will use a subscript S or K to tell us which type of friction force we are talking about. So what's the difference between static friction and kinetic friction? Let's say I start pushing on the box. I'll include a new force in my diagram showing me pushing on the box, trying to push the box to the right. If the force I exert on the box is relatively weak, the box won't move. There must be a friction force that's holding the box in place. Notice that in this case, the friction force is opposing my attempt to push the box to the right and points back to the left. Whether this is a force of static or kinetic friction depends on whether the box moves relative to the table. Static friction occurs when there is no relative motion between the surfaces in contact. If I push on the box and it doesn't slide across the table, static friction must be holding the box in place. But as I continue to push harder on the box, at some point it will begin to move. Once the box is moving relative to the table, there will be a force of kinetic friction that opposes that motion. So initially, static friction holds the box in place, and there is some maximum static friction force that I need to overcome to get the box moving. But once the box begins to slide, kinetic friction now acts on the box to oppose its motion rather than static friction. So what is the label I should give to the force I exert on the box as I push it to the right? In pushing on the box, I have put my hands in contact with the box, so this is really just another contact force between surfaces. However, we will typically refer to this kind of force exerted on the box as an applied force. We will often label additional forces that push on an object as applied forces, particularly when we don't want to confuse them with another normal force that is already in our diagram. So let's say I get a friend to help me move the box by attaching a rope to the front end of the box and pulling on it. In this case, the rope will exert a tension force on the box. A tension force is the force that is transmitted through a rope or a string or a cable or a chain as one object pulls on another. The tension force is always directed along the rope. Now let's change the scenario a little. My friend will continue to pull on the rope, dragging the box to the right. But now let's attach a spring to the left side of the box. The other end of the spring is attached to a wall, and as my friend pulls the box to the right, the spring stretches. In that case, there would be a new force, the spring or elastic force, that would pull the box back towards the wall. The first non-contact force we will deal with is the gravitational force. When people talk about an object's weight, they are talking about the gravitational force exerted on the object. An object feels a gravitational force not because it is in contact with another object, but because it sits in a gravitational field. Just like any force, I need two objects to be interacting to have a gravitational force. For an object sitting in the Earth's gravitational field, the gravitational force is the interaction between the object and the Earth. The Earth pulls any object, like the box in our example, straight downward. Unlike the contact forces that act on the box at its surface, where the table or spring or rope comes into contact with the box, the gravitational force acts on the center of mass of the box. There are two additional non-contact forces, the electric force and the magnetic force, but these forces we will save until we deal with electromagnetism next semester. All of our non-contact forces are related to something called a field. For the moment, we will simply highlight that for each of our non-contact forces there is a field that you have most likely heard of, the gravitational field, the electric field, and the magnetic field. How each of these fields creates a force will be a major idea we will investigate later in the course. We spoke briefly about notation earlier. Often we will just indicate the type of force when we label it in our diagram. But we could use a more complete notation that gives us more information about each force. Specifically, we can be more explicit about the two objects that are interacting through a particular force. For each force, we can indicate the type of force it is, the object that the force was exerted on, and the second object that exerted the force on the first. The weight of the box is a gravitational force exerted on the box by the Earth. The normal force in our diagram is the normal force exerted on the box by the table. The force of kinetic friction is the force of friction exerted on the box by the table as the box slides. The tension force is the force exerted on the box by Fred as he pulls on the rope. And the applied force is the force exerted on the box by Barney as he pushes the box to the right. Notice that every force in our diagram acts on the box. One of the most important tools we will use to think about forces is a free-body diagram. A free-body diagram is the vector diagram showing all the forces acting on an object. It will be critically important to recognize that forces that act on different objects belong in different free-body diagrams.